My name is Boris from the Toloka crowdsourcing research team. I still haven't learned the name, as you can see. Today, I would like to tell you about a very cool experiment and a prototype that we managed recently. It's about, as you might have guessed from the title, automatically optimizing quality control in data labeling pipelines. So here we go. As you might have heard, Toloka is a data labeling platform. It approaches the problem with crowdsourcing, and the usual process is like this. So you have some kind of a task. A task can be an image to be labeled, a class to be found for this image, maybe some text to be labeled, or basically anything. And you give this task to multiple annotators from an anonymous crowd. They give their answers to the tasks you have given them. You give them instructions, you configure the whole pipeline so that they understand what you want from them, and you get a few labels from them. But all of them are slightly unreliable because, unlike with in-house data labeling, you do not control the quality of what people are giving you, but you still have to pay them. So what people usually do is ask multiple annotators to give their answers and then aggregate them. And then you get one label. Aggregation can be as simple as majority votes. So if 2 people out of 3 think this image is a cat and your task does involve cats, then you say, okay, this is a cat. And then you train a model in. The problem that commonly occurs when you try to do this is that you have to make sure these answers given by people are reliable, because garbage in, garbage out is especially prominent in data labeling and when dealing with ML models, because they will learn everything you give in the data, even if it's very bad and not what you want at all. And so quality control happens. It's quality controls involves all of the things you do to make sure the labels are reliable. And there are ways to do this. So the simplest one is asking more people the same task. So that's called overlap. And it's the basis of any kind of crowdsourcing. But also you could do other things like filters. You could filter people based on age. You could filter people based on various stuff. You could introduce a training. Actually, you always do in practice. You could give them some tasks with answers that they can see so that they understand what you want from them. And finally, you have blocking. So in case people that are unreliable made through all of your filters and training and so on and started labeling your data, you can use some rules that will ban them when they make a few mistakes that you can detect. The simplest one is probably banning people for answering too fast. So you decide that it's impossible to do your task page, like say labeling 6 pictures in under 10 seconds, and you decide to ban anyone who answers, say, 3 times out of 7 faster than 10 seconds. So you have all of these rules, and the quality control is required. It does work, but what you get in the end is, well, you can see the picture on the right. It has so much numbers and it has so much configuration. It actually hurts anyone who tries to do data labeling, but you cannot do it without. Moreover, when you have quality control, you kind of want to make it strict because most people would rather have better quality, so more accurate labels, but you're paying with either money. So if you ask more people, you have to pay more people. For example, overlap being the most expensive one. And you're also paying with speed. So a balance has to be found. And in practice, nobody knows how to do it properly. So quality control is really hard because you have all of these parameters. This one is probably the most common and the most overused quality control in Toloka. And you can find the same thing in Amazon Turk, in any data labeling platform. It's the basis of quality control. It's control tasks. So basically, when a person is given some task to label, you give him, say, 5 pictures, and one of these pictures is something you know the answer for, but you do not tell the person who is labeling which is which. For him, they're all the same. However, later you can check his accuracy on these control tasks for which you do know the answers for. And this sounds good in practice, but in reality, you have to answer a lot of questions, like how many answers should be incorrect for a person to be banned, over how many task pages completed. Like, do you ban the person on the second mistake, on 2 consecutive mistakes, on like 1 out of 3 out of 5? So in the end, you get this this form to configure it, or maybe an API. Doesn't matter. What matters is that you have a lot of weird numbers you have to configure, and you have no idea how. I certainly don't. And it gets worse when you have a more complex project, when you need to configure 3, 4, 5 of this. So it's pretty complicated. We started investigating, like, how do people usually approach this problem? And we have found this to be the best practice. So basically, you smash your keyboard a few times until you have something quality control configured. And then you start labeling and you check the metrics. You see, is it even remotely okay? If it is, well, then you probably fiddle a bit more. If it's not, you certainly fiddle a bit more. But what's the most important thing is that after a few loops of this trying stuff, seeing if it works, trying stuff, seeing if it works with no clear feedback, most people just give up at some point where it seems good enough. And so people try stuff until it works, not until it's the best labeling pipeline for this task, not until the quality is the best or anything, because it's really tiring and it's hard. And we thought, why not just automate it? If people are just trying stuff and seeing what works, how about we have machines try stuff and see what works? And so the more ML educated among of you would probably think about hyperparameter optimization. And this is it. So we decided, how about we just try random search? And this is how our new method, auto quality, has been born. The idea is super simple. So let's consider a lot of different parameters, try them, see which of them obtain the best labeling quality we can get among, and pick this as the best. So basically, do what people are doing, try stuff until it works, and that's it. To be precise, so we define some distribution for each parameter. One example is on the picture on the right of the slide, where we are optimizing this, how many control tasks a person has to fail for him to be banned for the day. We define that, okay, usually we want, well, say the mean of this bell curve should be somewhere around 40% or so, where we want to ban a person if they're failing over 30% of the control tasks. But we also want our algorithm to try different ways. So we define this bell curve that basically says, okay, when we are going to pick this golden set incorrect answers rate parameter, more likely we'll get something between 20 and 60 maybe, and very unlikely we'll get something on the edges like close to 100, where the person has to get everything correct, and close to 0, where whatever the answer is okay. And we do introduce the same like curves or whatever distribution, our assumption about what parameters are common and what are not, which are not, for all kinds of parameters we have. So all thresholds, well, you'll see later. And then after we have defined this, we can sample from them. What happens is that we effectively do a grid search. So we sample a lot of parameters, but among this, usually we'll get golden set thresholds in the common ranges, with the algorithm only sometimes trying uncommon things, but still trying them. So if they work for this task, well, that's good. We'll stick with these parameters. So essentially try stuff until it works. But there is a complication. How could there not be? So imagine you had 4 of these little pools. You sampled some parameters, you put, say, 200 tasks into each. You did some labeling. You didn't spend really too much money on it, but you have some statistics. So you have pools A, B, C, D. all of which parameter sets. And for them, like pool A was the most heavily configured one. It had an overlap of 7. So for each task, 7 people were asked, and you obtained some numbers for each of them. Say accuracy on control tasks is 90% here and 86% here, and so on. How do you decide? How do you pick? So which are the best ones? You have accuracy, and more is better, of course. You have all these consistency metrics, which can be computed without labels, just based on how people agree with each other. More is better too, but you also have spending where more is worse, and you have labeling time, which you also want to minimize. We found, we tried quite a lot of complicated stuff, but we found a simple solution to work elegantly really well. So basically, let's rank all the stuff that we value. So for example, we take quality as a mean of accuracy, consistency, and blah, 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 all the metrics that define the accuracy of labels. And we rank all parameter sets based on their quality, with bigger being better. So for example, A has the best quality, it has the best accuracy, the best consistency, and so forth. And we assign it a rank of 4. The next best thing is B, and it gets a rank of 3, and so on. So this way we complete this column. We do the same for spending, where a bigger rank is better, where the most heavy parameter set A turns out to be the worst. And we also do the same for speed. So we also rank speed, making sure that a bigger rank is assigned to the faster pool. What we get is that now we have some ranks that define just how well did each pool do compared to others. And we can then take the average rank, and we get a number that indicates just how good is the pool on average in all of these 3 qualities. What happens is that, as you can see, the A pool with the abnormally high overlap, it received a not so high rank, which is good because we really don't want to pick whatever pool had the highest overlap, because we don't want to waste too much money. As you can see, A, to get a slightly bigger accuracy, had to spend like over 3 times more money than the next best thing. So we probably, the most people would rather sacrifice a little bit of accuracy to save 3 times the money. However, we have found that just averaging is not clever enough, so we performed some more clever averaging. The reason being is that actually for most people, quality is way more important than, say, spending or speed. But we also don't want to completely throw away spending, because then our algorithm will pick simply based on overlap, which always correlates with higher quality. The problem is that at some point it's not worth it, and we use spending and speed ranks to understand when. What we found is that when we just average stuff, we implicitly introduce this assumption that all things are equal. All criteria, the quality, spending, and speed are equal. That's not true. And so we do some more clever averaging where we just assign custom weights. So quality being the most important thing, and then spending, and then speed. And these weights can be configured based on the task and the requirements of each problem. After we have assembled this prototype, we tested it on an internal benchmark. It's the scientific data set called IMDB movie reviews. It's very simple. You have movie reviews and you have to classify if they're positive or negative. And we first tried to handpick the best settings we could, and we found a really good result where we have almost 90% accuracy with an overlap of 5. However, when we ran this automatic method, we found that it found almost, a very close accuracy, so 85%, but with over 2 times less the overlap, so 2 times the money saved. And it was a really surprising result, because it only took us a tiny bit of examples to obtain these parameters. We have spent only like $3 to get it, and only like 15 minutes. instead of spending a few hours optimizing it all by hand, running it repeatedly, losing money every time, and so forth. That was really good. We investigated the settings found, here they are, and what I want to point out is that they're like okay for the most part. So for example, it has fast responses with banning people for providing a lot of fast responses. The task is not hard, so usually all the competent people, they do not submit a lot of fast responses, so just banning people that got all of them incorrect cleared out the completely fraudulent annotators. It also had a very sane approach to control tasks and banning by control tasks. But what was surprising is that we had an overlap of 2 as a result. It was included as a kind of just for fun to see if the algorithm will ever pick anything under 3. Usually you ask at least 3 people, because in case of a majority vote, you don't want a tie. But what we found is that the algorithm actually picked an overlap of 2. And that was because any more was not worth it. Still, some of the settings were really surprising, like the majority vote where just disagreeing with one person would be considered well, you had to disagree 8 times, like 4 times to 3 or 4 times to get a ban, but still having an overlap of 2 and a majority vote, that was weird. So after this, we have refined the method, but still it was really interesting that the settings that were found were very counterintuitive to people, but still they did work. And when we tried them on longer task, it was proven again. So after we were done with the internal benchmarks, we went on to one of the Toloka requesters, people that do actually label real world data in Toloka, and asked them for some task we could test it on. So this was the task. The company does e-commerce data analytics, and they have this task where you have an image of a photo taken by a user of some album cover, and you had to identify if one of the provided album covers was on this photo. A really simple, sort of like an image classification task. We eventually reframed it to image classification. The initial quality settings that this requester had, they were same. So an overlap of 3, and a threshold for exam and training, banning people for fast answers, banning people for disagreement with majority vote. However, you had to disagree completely, and banning people for any mistake on any control task. So these are pretty normal settings. What we got with our method was again very surprising. So an overlap of 2 and no quality control, in the sense that you only have strict training and some exam, and that's it. We were very surprised, to say the least, that yeah, by this time we have refined our method such that if nobody has been banned by some quality control, then it was removed from the eventual set. So no more fast answers if nobody has been banned by fast answers. But when we so we were really skeptical about this one, like how can you have no quality control? And we decided to do a fair experiment. So we have taken a bigger holdout set of tasks, and we had the requester, the company, and us label it separately with the settings that we have, just so that nobody had the true labels and everything was fair, and so forth. What we found out is that our method with these weird settings has spent 2 times less money about the same time. And well, actually, no, it's 2 times less time as well. And it just didn't ban anyone. And the metrics were better. Well, wait, no, here I'm wrong. They were not better. As you can see, the company had for their expense slightly bigger consistency. But we had the slightly bigger Krippendorf alpha, which means that probably the quality was about the same. And so when we investigated how could this happen, that no quality control was better than some quality control, some strict quality control, we arrived to the conclusion that in fact the task was so simple that just having a good training, some exam, and it was enough. We expected to be improving someone's quality with this method, but what we found is that naturally people tend to overcomplicate this complicated forms with all of these parameters. And auto quality didn't, in this case, find a better quality control because it could not be found. The task was already basically solved. Well, or we have not managed, of course, that's still the possibility. So the mental question I want to ask everyone is that, would you pay in, of course, data labeling costs, a few dollars to not do quality control? As for me, I'm certain that I would, because it is annoying to do, but it's still very important, so you cannot skip it until now. Having told this, I would like to address some limitations of this upcoming thing. The first one is that if you have some kind of a complex case, auto quality will only partially help you. So it can, as it only does trying stuff and checking the metrics, and that's it. It cannot cover any kind of multi-stage projects where you have post accept or annotators checking other annotators. You can configure some of this, parameters in these pipelines, but at this point, you are probably better off doing it yourself. However, it's still good for classification tasks, the most common tasks, and so on. Also, another big concern now that we're investigating is that we do know that quality control settings in the real projects, they tend to degrade over time. So this company, for example, told us that when you release some new control tasks, suddenly your quality goes down, the accuracy on control tasks. And that means that people do adapt to the stuff you have, to all the ban rules you have, the control tasks you have. And we currently do not know how will this auto quality found and sometimes weird parameters behave in the long run. So this remains to be investigated, but what we arrived to currently is that in the worst case, you can just configure them slightly by hand, as you do with the hand-picked parameters. And also you could rerun the algorithm to get something better. Well, and the final concern is that the algorithm is stupid, unlike people. And so it will pick sometimes stuff that's very counterintuitive and might as well be wrong, such as a majority vote where you don't need one, simply because we have not at the moment added the ability for it to not include a majority vote ban at all. So it will do stupid stuff. And so you should always check what it outputs you. So currently it's a prototype, and we have devised this prototype. Let me summarize it. So we have made a few fun experiments with automatically configuring data labeling pipelines. It seems to work well. It does find counterintuitive stuff by just trying different, very likely sets of parameters and picking whatever has the best metrics. We tested it currently on internal benchmarks. I have not named all of them, but trust me, there were a few. And on one external real data labeling task. We are currently testing it more. So maybe we'll see it as part of a product. But one should, so this is a simple method. It's very easy to actually apply and implement if you want it. Just be careful that the long-term efficiency of this, it's still not studied well.